Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. In the last video, we introduced the formal definition of a derivative, and we will continue to explore this idea a little further today through some more examples. But before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. So let's jump straight into our first example, which is to use the definition of a derivative to find f prime of x. So we know that the definition of f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So our function f of x is x to the power of 2 over 3. So let's go ahead and substitute that in. So we get this is equal to the limit as h approaches 0 of, and we're going to get x plus h to the power of 2 over 3 minus x to the power of 2 over 3, and we have this is over h. So here it looks like we might be a little bit stuck because we can't expand this part and we can't cancel the h on the bottom. But what we're going to do is we're going to use a little trick here. We're going to use the identity that a to the power of 3 minus b to the power of 3, so difference of cubes. We know that this is equal to a minus b times a squared plus ab plus b squared. And then we're going to let a be equal to x plus h to the power of 2 over 3. And then we're going to let b be equal to x to the power of 2 over 3. So essentially, our numerator here is just a minus b. And then what we're going to do is we're going to multiply both the numerator and the denominator by a squared plus ab plus b squared. So then what that means is we're going to get a cubed is going to be equal to x plus h squared, and b cubed is going to be x squared. So once we do that, then that means our numerator is a cubed minus b cubed, so that's going to be x plus h squared minus x squared. And then our denominator is going to be h times, and then we need to multiply it by this part. So that means this is going to be equal to a squared, so that'll be x plus h to the power of 4 over 3, and then plus a times b, so that'll be x plus h to the power of 2 over 3 times x to the power of 2 over 3, and then plus b squared is going to be x to the power of 4 over 3. And let's just go ahead and extend this line a little bit further. So I know the denominator looks a little bit messy right now, but we don't really actually care about that because eventually we're going to take the limit as h goes to 0, and that's going to simplify a lot of these things here. What we care about is we want to expand our numerator so that hopefully we can cancel out with the h in the denominator. So if we were to expand our numerator, we're going to get x squared plus 2xh plus h squared, and then we have minus x squared. And then our denominator is going to stay the same. We're not going to simplify it. So that's going to be h times, we have x plus h to the power of 4 over 3 plus x plus h to the power of 2 over 3, x to the power of 2 over 3, and then plus x to the power of 4 over 3. So now we can see that for our numerator, we have an x squared term minus an x squared term. So that means they're going to cancel out. And then the two terms that we're left with both have at least one h in there. So that means we can go ahead and factor that out. So then we get this is equal to the limit as h approaches 0. And then now our numerator is going to be h times 2x plus h. And then again, our denominator stays exactly the same. So we're just going to write that out one last time. And then once we finish writing this out, we can go ahead and cancel out the h that is on top and then the h that is on the bottom. And once we no longer have our h in the denominator, we can go ahead and take the limit. So once we cancel, we can say this is equal to, and once we take the limit, our numerator is going to be 2x, and then our denominator is going to be x plus 0 to the power of 4 over 3, so that's just x to the power of 4 over 3, and then we have plus. This is going to be x to the power of 2 over 3 times x to the power of 2 over 3. So we can go ahead and add the exponents. So that's another x to the power of 4 over 3. And then we have one last x to the power of 4 over 3. And then combining our like terms on the bottom, we end up with this is 2x over 3 times x to the power of 4 over 3. And then now just the last bit, we can cancel out an x on the top and an x on the bottom. So therefore, our final answer is going to be f prime of x is equal to 2 over 3, and then we have x to the power of negative 1 over 3. And now let's go ahead and take a look at the graph of our f of x and f prime of x to see what kind of pattern we can draw from it. So here, the red graph is f of x. So I've plotted this in Desmos already. And then the blue graph here is our f prime of x. So recall that the derivative, f prime of x, gives you the slope of f of x at each x value. So let's say we pick this point here, and then we draw the tangent line to that point. That's going to give us the slope at that point. So there, the slope is negative. And that is what this value here tells us. So the y value here gives us the slope at this point here. And then as we move down this curve, we can see that the slope is getting steeper. It's getting more negative. So let's say if we were to pick this point here, we can see that the slope there is going to be more negative. And that is why the value of f prime of x at that point is going to be a more negative number compared to this earlier number here. And then what happens when we get closer and closer to 0 is we can see that it almost looks like it's going to become a vertical straight line, which is why f prime of x looks like it is dropping down all the way to negative infinity. And then if we go ahead and look at the other side of f of x, so the other side of 0, we can see that it is a positive slope that looks like almost a vertical line, which is why we have our f prime of x going towards positive infinity. And then as we travel along the curve, we can see that the slope gets less and less steep. And that is why f prime of x is decreasing in value and it's becoming a smaller and smaller positive number. But it's still positive because the slope here is still positive. So the key ideas here is that when f is increasing, f prime of x is greater than 0. And this is because f prime of x tells you the slope. So if f is increasing, then we have a positive slope. And where f is decreasing, f prime is going to be less than 0. That means it's a negative slope. And horizontal tangents are when f prime of x is equal to 0, because that means the slope there is 0. And finally, a steeper graph means a larger magnitude of the derivative. And now let's go ahead and use that knowledge to sketch the graph of f prime of x. So here we're given the graph of f of x, and we're asked to sketch the derivative. So the important points here would be to find first where the slope is 0. So that would be right over here and right over here. These are where we have our horizontal tangents. So right there and right there. So that means if it's horizontal tangent there, then f prime of x must be equal to 0 at those points. So the first one is roughly around -2, and then the other one is around +1. So that means for f prime of x, we're going to have a value of 0 at those two x values. So now if we look to the left side of -2, we can see that our graph is increasing. So here we have positive slope. In fact, it starts very positive because it's very steep, and then it gets less steep, but then it's still positive until it reaches an x value of -2, where it has a horizontal slope. So that tells us for our f prime of x, we're going to have a very positive value, and then it's going to be a little less positive, a little less positive, until we reach -2, and that is our 0. And then what happens after that is we can see that we're now starting to go downwards. So this is going to be negative slope. And then in fact, from -2 to +1, we always have a negative slope. The only difference is that it's a little less steep here, and then it's also a little less steep here. And then in the middle, around this part, it is more steep. So when it's more steep, it just means that it's going to be a larger negative value. That means when we're drawing our f prime of x, we're going to have a smaller negative value, a larger negative value, and then a smaller negative value. And now finally, the last part of this graph, right over here, we can see that we're again back to having a positive slope. And we start off less steep, so this is a small positive value, until we get here, and this is a much steeper slope, so that means this is going to be a much larger positive value. So to continue our graph for f prime of x, it would probably look something like this. And now we're going to take a small break to talk about notation. So far, we've been using f prime of x as our main notation when we talk about derivative. But all four of those can be used. So this would be y prime. This is what we call dy by dx. And this is d by dx of f of x. And all of them mean the same thing. The special thing to note here is that when we say d by dx, you can think of this as a verb. So what this means is that it is the act of doing the derivative, whereas everything else we've talked about act as a noun. So for example, f prime of x means that it is the derivative of the function f with respect to x. And y prime means that it is the derivative of y. So this dy by dx here, you can think of it as it is d by dx, so meaning the act of taking the derivative of y. So then once we take the derivative of y with respect to x, we end up with a noun, which is the derivative of y with respect to x. And just a little tidbit, this dy by dx is known as the Leibniz notation, Leibniz being one of the founders of calculus. And now lastly, we've talked about how the derivative help us with the tangent problem through a few examples in the last video. But let's finish this idea off with the relationship to the velocity problem. And we're going to do that through this fourth example here. If an arrow is shot upward on the moon with a velocity of 58 meters per second, its height in meters after t seconds is given by this equation here. So now the first part of the question is to find the velocity of the arrow when t is equal to a. And we're going to be doing that using the definition of a derivative. We're going to call our velocity v. So v of a is going to be equal to the limit as h approaches 0 of h of a plus h minus h of a over h. So here the capital H is our function here, and then the lowercase h is that distance between the 2 points that we're picking, which we talked about in the previous video. So now let's go ahead and substitute our function in. So this is equal to limit as lowercase h goes to 0 of, now capital H of a plus lowercase h, that is going to be 58 times a plus h minus 0.83 times a plus h squared. And then we are going to be subtracting h of a So that is going to be 58a minus 0.a3 a squared. And this is over lowercase h. Okay, so we're going to now go ahead and expand everything on the top. So we get limit as h approaches 0. And then the top is now going to be 58a plus 58h minus 0.83a squared minus 1.66ah and then minus 0.83h squared. So that is expanding out the first square bracket. And then we're going to subtract 58a, and then we're going to distribute that minus sign. So this ends up being plus 0.83a squared. And then this is over lowercase h. And now we can go ahead and cancel out some terms on the top. So we have a 58a minus a 58a. And then we have a negative 0.83a squared and a positive 0.83a squared. So after canceling out those terms, we're left with limit as h approaches 0 of, and then we have 3 terms left, and all of these terms have at least one h in there. So let's go ahead and factor that out. So we get h times 58 minus 1.66a minus 0.83h. And then we have this is over h. And now we can go ahead and cancel out the h on top and bottom. And our final answer, after we take the limit, this is going to be equal to 58 minus 1.66a. And let's actually go ahead and add units here. So because this is velocity, so v of a, this is going to be meters per second. Part B is asking, when will the arrow hit the moon? So imagine if you're shooting this arrow up, eventually it's going to fall back down. And when it hits the moon, it is going to have a height of 0. So in other words, for part B, we're just trying to find t when h of t is equal to 0. So we want to solve for t where h of t is equal to 0. So that means we want 58t minus 0.83t squared to be equal to 0. So we can go ahead and factor out a t. And then we get t times 58 minus 0.83t is equal to 0. So one solution is going to be when t is equal to 0. And that makes sense because that is when you're firing the arrow, but it's the other t that we're interested in. That is going to give us the time t when the arrow hits the moon again. So that one is going to be t is equal to 58 over 0.83. And that is roughly 69.88 seconds. Okay, and now part C, it's asking, with what velocity will the arrow hit the moon? So meaning, when the arrow comes back to the moon, what is the velocity of the arrow? Well, we know that it's going to hit the moon at 69.88 seconds. And we already have the equation for the velocity of the arrow at time A. So all we need to do is substitute this value into our velocity equation. So part C, what we're looking for is we're looking for v of 69.88. So that's going to be 58 minus 1.66 times 69.88. And this is going to give us roughly negative 58 meters per second. So now a quick note on the sign here. It is negative because the arrow is falling downward. So therefore the velocity is negative because velocity has a direction to it. And now let's do a recap of what we covered in this video. We saw how derivatives can be computed directly from the definition. And there are multiple different ways of writing the derivative, but all these different notations describe the same concept. We saw how graphs of derivatives represent slope behavior, and we went through an example of drawing the f prime of x given f of x. And finally, we connected derivatives to the velocity problem. We saw that velocity is a real-world derivative. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.